extremely very sorry, there was internet connectivity issue. So yeah, let's just start our session for today. Let me present my screen. Let me present my entire screen. So yeah, I hope my presentation is visible. So let me just check whether my presentation is visible. Yes, so it's visible. So yeah, let's start our session for today, and I hope that I am audible to everyone who is here today. Yeah, so let's just start our session for today without any further ado. Good evening everyone. Today we are here for the week 8 live interaction session for the course on renewable energy engineering, solar, wind and biomass energy system. I am Pratyumnan, a PhD student in the Department of Chemical Engineering, IIT Guwahati, is a course team member who is responsible for conducting the weekly live interaction session. This course is offered by Professor Vaibhav Vishant Gaut sir and Professor Anandalakshmi ma'am from the Department of Chemical Engineering, IIT Guwahati, under the NPTEL program. So we have come so far like 2 weeks of biomass sessions. If you remember, the last week and the last to last week, we dedicated our focus towards understanding how biomass is an energy resource, how biomass is a renewable energy resource, and how we can use biomass for our energy application, its different form, and how it's a cleaner source of energy, how sun is directly or solar energy is directly contributing to the biomass energy harnessing, and we also discussed about the biomass characterization, where we dealt in depth with the proximate analysis and the ultimate analysis of the biomass, its characterization, how to identify the percentage of fixed carbon, percentage of moisture, percentage of ash in the biomass sample, and then towards the ultimate analysis we identified how to find the percentage elemental composition in our sample, like percentage of carbon, percentage of nitrogen, hydrogen, percentage of sulfur. We focused on these two aspects in the previous live interaction session. So if you remember, we discussed about the various kind of analytical techniques that is present in order to determine the percentage of carbon, percentage of nitrogen. For example, for percentage of nitrogen we use the Geldal method. For percentage of sulfur we use the barium sulfate. We use the barium chloride solution and then allowed the barium sulfate to be precipitated. From there we identified the percentage of sulfur in the biomass sample. Similarly, with percentage of carbon and hydrogen, we identified them using KOH as well as the CaCl2 compounds. We identified the percentage of carbon and hydrogen in the biomass sample, and then we discussed about the different ways or different ways this biomass can be converted to biofuels. We discussed about two different ways. One is the ethanol fermentation and the other one is the anaerobic digestion. So when your biomass is going to undergo anaerobic digestion using microbes, your biomass is actually going to convert it to biogas, which is nothing but it is a composition of both your methane as well as that of your carbon dioxide. So this is what we discussed till the last lecture. In this lecture we will focus on how to design a plan for the production of biogas. Like, we are going to synthesize the biogas using the biomass, and this is going to happen inside the digester. So how to design the digester? What will be the height, diameter of the digester? How much amount of the biogas will be produced, or what should be the size of your biogas digester to release this much amount of biogas or to accommodate this much amount of biogas? We will discuss all these design principles for the biogas digestion plant in this week 8 live interaction session. So before moving on to that, let us just revise or have a recap of what we discussed previously in detail as such. So here if you see, you have a biogas digester plant. So this biogas digester plant, if you remember, we discussed about two different types of biogas digester plant. One is the floating drum and another one is the fixed dome type model. So if you see here, this is a typical biogas plant design, but I would like to know from you guys, because since we have discussed this in detail previously in the week 7 live interaction session, I'd also like you to tell me what biogas plant is it. Does it comes under the category of floating drum or the fixed dome? Anybody? Okay, so if you see here, this is nothing but it's a fixed dome. In case of a floating drum, if you remember in our previous live interaction session, instead of a wall that is actually created, this arc, we had a drum placed on top, and that was a floating drum. So as far as the construction of a biogas plant is concerned, the only difference that exists between the fixed dome and the floating dome is the presence of a floating drum in case of your floating drum type biogas plant, and a fixed dome, that is the fixed arc wall that is constructed on the top. If you see, this is the fixed dome type biogas digester plant. So as far as the construction is concerned, the difference between them is the presence or the absence of the floating drum in their design. Apart from that, if you see, everything else actually remains the same. So you have a mixing tank, and then you have an inlet chamber, and then this slurry is created. Usually slurry is nothing but it is a composition of both your biomass as well as that of the water. These both are mixed here in this mixing tank as an inlet, which is then fed to your digester tank. Inside the digester tank, there will be a agitator or kind of a stirrer, which will help you in mixing the biomass with the microorganisms that is already fed into your biodigester, and then this biomass will be present in your biodigester for a certain period of time. After the digestion and the release of the biogas, that is nothing but your methane and the carbon dioxide predominantly, this biogas, this biomass, the spent or the digested biomass will move to your outlet chamber and then to the spent slurry. From this overflow tank, you can collect the spent slurry or the digested biomass, and this will be rich in the nutrients, so they can be used as a manure or kind of a fertilizer for your agricultural fields. And then the generated biogas, depending upon the need, using a valve, it will be collected from the outlet, and this biogas will be then used for many varieties of applications such as lighting, thermal applications, cooking. In majority of the village homes, this biogas plant will be helpful for cooking, and then even in some cases like engine applications also is possible using this biogas digester plant. So in India, if you see this biogas digester, the most common or the famous two examples that is present in the literature will be your floating drum, that is nothing but your KVIC design, and then your fixed dome, that is nothing but the Deenabandhu design, which is installed in India in 1984 in New Delhi by the Action for Food Production organization. So these are the two famous designs for the floating drum and the fixed dome in India. So if you see, the fixed dome as well as that of your floating drum has pros as well as cons. So each of them will be suitable for different applications or different conditions, and we should have awareness or we should have knowledge about where to use this floating drum biogas digester plant and where to use the fixed dome biogas digester plant. So if you see the advantages associated with your floating drum, so since you have a floating drum on top of your biogas plant or this biogas digester or this chamber, so there will not be any kind of problem for gas leakage. And another one more important difference if you see between the floating drum and the fixed dome is the principle, the mechanism principle with based on which these two digester plants operate. For example, if you see floating drum over there, since the drums keep floating depending upon the gas generated in the digester, so it will be a constant pressure biogas digester plant. In case of a fixed dome, what happens is the volume will be fixed because it's a arc wall which is constructed, and that cannot move, it is stationary, so the volume will be constant in case of a fixed dome, whereas in case of a floating dome the pressure will remain constant. So that becomes one of the advantages of a floating drum. So there is no problem of gas leakage in floating drum, there is a constant pressure in the floating drum, and then the amount of biogas that is generated per unit volume of your digester will be high in case of floating drum compared to your fixed drum. But it also has its own disadvantages. One of the main disadvantages is that the high cost. So your floating drum has an additional provision of using a floating drum on top of your digester, so that incorporates the cost of the biogas, so it will increase your cost of the digester plant, the setup cost, and also the metal gas holder that is placed on top of your floating drum, from there the heat loss can happen. So these are the disadvantages associated with your floating drum. In case of your fixed dome or fixed dome type biogas plant, what are the advantages is that it is of low cost. So unlike in case of your floating drum, which requires additional setup and that requires more amount of money to be spent on the initial setup, in case of a fixed dome type biogas plant the cost will be low, and it's also non-corrosible, the temperature remains constant, and then the heat insulation is provided. So in this case of the fixed dome biogas plant, if you see in the left hand side it is mentioned ground level. So this fixed dome biogas digester plant is usually constructed under the ground level surface. So it is not present at the top or above the ground level, but it is present below the ground level. So due to which the heat insulation will be good. But the disadvantages associated with the fixed dome type biogas digester plant is that the amount of gas produced will be less, and the pressure that your wall is going to face at every instant of time, if you check, will be varying because your volume is going to remain constant. So biogas will keep getting generated and that generation will not be constant, it will be variable. So your fixed dome or the arc wall that has been constructed will be subjected to variable gas pressure. So that becomes one of the disadvantages, because there can be chances of a crack that is getting formed due to the variable pressure. So your wall, the dome which has been constructed at the top, will be subjected to variable pressure, so due to which crack formation can happen, and that will lead to the failure of the plant. So these are the advantages and disadvantages associated with these two types of biogas digester plant, the floating drum and then the fixed dome type plant. So when you are going to feed in your biomass inside this digester plant, there are various factors that will affect your yield, how much amount of the gas is going to get generated from their biogas. So you need to optimize these parameters, because anything that will less than what it is required, or if it is in excess of what is required, will be harmful to the process in general. So similarly here also there are a lot of factors that affects your biogas yield, and you need to really optimize each and every different parameters that you see here to increase or maximize the production of the biogas that you get from the amount of biomass that you feed to your digester. So our main focus or our main goal is to extract more amount of biogas, or is to extract as much as biogas possible from 1 kg or from whatever amount of biomass that we are going to feed into the system. So we, as such, our intention is to enhance the biogas generation, the amount of biogas that is getting generated with a very small volume of your biomass that is fed to the digester plant. So there are various factors that are listed here. So you have temperature, pressure, loading rate, carbon nitrogen ratio, pH, hydraulic retention time, seeding, effect of toxic substance, and the raw material type or the availability of the raw material. So we will discuss each and every different factors here in detail today, because we were unable to cover this section of the biogas digester plant last week. So we will be taking up with this factors that is affecting the biogas yield in this week 8 live interaction session. So the first and the most important factors that affect your biogas yield is nothing but the temperature of your biogas digester plant. So the optimum temperature at which your biogas digester plant is going to operate is approximately between 35 to 40 degrees Celsius, and at 30 degrees Celsius the amount of biogas that is going to be generated will be maximum. One of the reasons why this happens is basically because of the types of microorganism that is grown or that is fed to the that is fed on the biomass. So these microorganisms usually work well only in this temperature ranges, and at 35 degrees Celsius the amount of microbiological activity of the microorganism on your biomass is going to be at the maximum. So that is the reason at 35 degrees Celsius the amount of biogas that is going to get generated from your biomass will be maximum. So here the slurry and the water is fed, and then the microbes are usually grown inside the digester, and by stirring the microbes and the slurry gets mixed properly, a uniform mixing is obtained, and then the bacteria feeds on the microbe feeds on the biomass, and then it actually undergoes hydrolysis, acidogenesis, and then the methanogenesis, finally releasing the methane as well as the carbon dioxide. So if you remember, in case of your biomass to biogas anaerobic digestion process, you have 4 different processes. One is your simple hydrolysis, which is nothing but breaking the complex biomass substance into simpler forms. Then comes is the acidogenesis, where the simple organic matter is converted to higher carbon fatty acids like butyric acids, and then it undergoes acidogenesis process, where this higher fatty acids or like higher acids like butyric acid is converted to acetic acid, which is then gets converted to methane through the methanogenesis or methanogens bacteria into methane and the carbon dioxide. So these microorganisms which are responsible for this anaerobic digestion or for driving the biomass to biogas conversion usually works well between 35 to 40 degrees Celsius. So the microbes here are of 2 different types, and this classification of the microbes that you see here or that we do here is based on the temperature. So the 2 classes here is nothing but is a mesophile and the thermophile. So let me just write that. So you have mesophile and thermophile. So what is the difference between your mesophile and the thermophile? It is nothing but it is the temperature range at which they work. So for a thermophile, if you see the optimum temperature range or the range in which they show their maximum microbiological activity is between 50 to 60 degrees Celsius, whereas in case of your mesophilic it is between 35 to 40 degrees Celsius. So depending upon the temperature that we want and about how to you and at what temperature we get the maximum yield, we choose the microbes used for this biomass digestion process, anaerobic digestion process. So here, I mean, I'm continuously saying the word anaerobic. So I hope everybody have an understanding of what anaerobic is. So please, can you let me know what do you actually mean by anaerobic and aerobic process? And I hope my screen is also visible. Yes, what is the difference between anaerobic and aerobic? So anaerobic is nothing but some kind of digestion or like something a process that usually happens. Yeah, you can unmute and let me know.
Sir, it is related to the presence of oxygen
Yeah, yeah, yeah. So
absence of.
mm, yeah, so in case of your anaerobic, it will be in a limited or no supply of air or oxygen, whereas in case of your aerobic, it will be in exact quantity of oxygen or in excess. So here we finish with the temperature, and here as such as I said, we will use mesophile and thermophile, two kinds of microorganism whose classification depends upon the temperature, will be used for digesting your biomass to biogas or methane as well as carbon dioxide. The second important factor that is affecting your biogas yield is nothing but the pressure. So if you see here, we have to optimize. This is a table or like a column which suggests what is the optimized parameters for your biogas digester plant. So your pressure is approximately, you have to maintain up to 1.2 bar so that there is a proper functioning of the biogas plant. So what will happen if in case excess pressure is there? So if excess pressure is there, then this will as such create any kind of damage to your biogas system, because more pressure, your wall is going to be subjected to more pressure from all the sides. So if your pressure increases, then there are chances of crack. Also it will lead to your release of gas from the slurry. So there can be a gas leakage also that could happen if your pressure is more. So this is the so that is why we need to optimize your pressure up to 1.2 bars. So that will be your optimized pressure which you need to maintain. Both excess as well as low pressure will not be helpful for our biogas digesting process. Next comes is your another important factor, that is nothing but your loading rate. So as such, if you see the name, it is loading rate. So the rate at which you are going to load your material. Load what material? Load your biogas or biomass material. So that is what is the definition. How much amount of your material is going to be fed into the digester per unit volume? So if you have some amount, how much you are going to feed your digester with that biomass per unit volume of your digester, that is your loading rate. How much amount of your biomass are you going to feed into your digester plant? So again, this has to be approximately between 1 to 4 volume kg per meter cube per day. So if excess loading is present, so what happens if you add more amount of your material? Let's say my biogas digester plant can accommodate only up to 4 volume kg per meter cube day, but let's say I feed 5, or let's say I feed 6, the loading rate I keep it as 6. So what is going to happen in that case? So what will happen is, if you are going to keep on feeding your biogas digester with more and more amount of your feed material, the amount of acid accumulation that will be happening will also keep increasing. So as I said, biogas will get converted to some sort of an acid, like either butyric acid or acetic acid, and then from there the methanogenesis process will happen, where they will release your methane. So if excess loading is there, the bacteria will keep on releasing this acid. acid generation will be more. So if the acid accumulation starts happening, then the bacteria will not be able to digest or break down this acid and release the methane. So digestion process actually stops and the undigested slurry will come out. So once the digestion process is going to stop, the amount of slurry that is remaining undigested will be more, because we are feeding in excess of what is required, or excess of what is needed. Yes, so the undigested slurry will be more. So majority of the slurry, whatever you are going to feed in, is going to just come out in the overflow tank. So your loading should not be excess. Okay, so now again a question arises: what happens if I keep my mass loading lesser than what is required? Again, if you keep less, what actually happens is entire digestion process will occur, but the amount of biogas that is going to be generated will be less. So if I have to, let's say for example, for 1 kg of biomass that I am going to feed in, I am supposed to get 0.5 meter cube of biogas. But if I feed less, then the amount of biogas that is going to get generated will be less. But the amount of cost that has to be spent for this process will remain the same. So you're going to get less biogas, but at the same time the amount of cost that is involved in this process will remain the same. Less biogas, but more cost, more more cost is going to be, more expenditure will be there, but the amount of biogas that you are going to generate will be less. So that will make the process uneconomical. It will not be something very feasible. We will be spending more amount of money, but then the return that we get from this biogas digester plant will be less. So that's a loss for us, and that is something that we do not actually want to happen. So if you load with a less biomass material, there will be a reduced biogas production, and that will make the process uneconomical. So if you feed in with excess, then what will happen is acid accumulation will happen, and that will drop down your digestion process, and majority of the slurry will be undigested slurry will come out. So your biogas production will also be less in that case, and whatever the slurry that is going to be overflowed in your overflow tank will be undigested, and it cannot be used for it cannot be used as a manure or fertilizer also somewhere. So that's a two disadvantages that is going to happen simultaneously. And if you reduce your loading, then the amount of expenditure that happens on this process will be more compared to what you can gain through this process. So that will also make the process uneconomical. So that also is a disadvantage. So that is the reason we need to optimize the loading rate, and this is one of the important parameters in the biogas digester plant. So the recommended would be this 1 to 4 volume kg per meter cube day. So that I will correct it afterwards. Yeah. So the next one is nothing but is your CN ratio. So here C represents for your carbon and N represents for your nitrogen. So how does this C and N ratio or CN ratio is going to affect the biogas that is going to get generated? How is it going to affect the quality of the biogas? So what effect does this carbon versus nitrogen ratio will have on the quality of the biogas that is going to get generated? So if you see, the quality or the amount of the biogas that will be generated in this process actually depends upon the microbes that you are going to use. So if you remember, we discussed about two different types of microbes. One will be the mesophile and the other one will be the thermophile. So the action of these two microbes should be more, their microbiological activity should be enhanced, should be more, then only we will be receiving higher amount of or higher yield of biogas. So these microbes are usually grown in the digester plant, and in order to grow these grow this, we actually require the nutrients. And the bacteria, this mesophile or the thermophile that you are going to use here, will take up 30 times more amount of carbon compounds compared to the nitrogen. So only when so they require nutrients to survive and thrive, and to grow and then do their digestion process, and they usually take up 30 times more carbon compared to nitrogen. So when they take up that much amount of carbon compared to nitrogen, then only their microbiological activity will be more. So these anaerobic bacteria which you are going to put here uses carbon based nutrients more for their survival. That is the reason why they take up 30 times more carbon compared to nitrogen. And when they do this, when they take up more amount of carbon, when more carbon is available to them, then only their microbiological activity will be enhanced. So you have to optimize the ratio of carbon and nitrogen between 30:1 or 25:1, that is 25 parts of carbon and 1 part of nitrogen, or 30 parts of carbon and 1 part of the nitrogen. The ratio can vary from 25:1 to 30:1, but only if it is in this range, then the maximum digestion will occur, that will lead to enhanced biogas production. So again, as we saw in loading rate, how if one thing is in excess, how it will affect our biogas yield. Similarly, we will also see what happens here if your carbon is more compared to nitrogen, that is very large, not just 30:1. If it is in a higher ratios of, let's say, 60:1 or more than that, what would be the effect of it on your biogas yield, and what happens if your carbon to nitrogen ratio will be very low. We will be seeing that now. So if your carbon present is in excess, let's say you have a very high ratio of carbon compared to nitrogen, lots of carbon is going to be present compared to the nitrogen that is available. In that case, what happens is these bacteria, they will first consume of the nitrogen. Whatever that is present in the lower quantity will be consumed up faster. So since the entire amount of nitrogen is going to get consumed up, but more amount of the carbon is going to be present, so both will be consumed up at the same rate, but since the carbon is more, lot of carbon will be present compared to the nitrogen. So if more carbon is going to be left over, then the digestion process will slow down. So since the digestion process is going to get slowed down, the amount of biogas that is going to get generated will be slowed down. But what is the case if your nitrogen is going to be more? Let's say the ratio is around the entire reverse ratio, 1:100, or let's say carbon 1 parts and nitrogen 30 parts. So in that case, since the bacteria is going to consume both carbon and nitrogen, the carbon will be exhausted first and lots of nitrogen will be present. This nitrogen and then the hydrogen that is present in your biomass, because hydrogen will be present in the biogas or biomass as such, so those two will react and they will form ammonia. N and H will combine to form your NH3, like N plus 3/2H2 will give you NH3. So ammonia will be generated, and this ammonia is toxic in nature, so that has the chance to kill the microbes or the anaerobic microbes or anaerobic bacteria that is going to feed on your biomass. So if it kills the bacteria, then the biogas will not at all be generated. So even at that time, majority of the slurry is going to be undigested and lesser amount of the biogas is going to be generated. So there will be two disadvantages that is going to happen simultaneously: low biogas production, low slurry for your low digested slurry for your manure or fertilizer for the plants. So this nitrogen, a carbon to nitrogen ratio also has to be maintained between 30:1. Coming to the pH, let me just give you some time, because we have discussed a lot of parameters: loading rate, carbon nitrogen ratio, and if you have any doubts, then please let me know. So here in the carbon and nitrogen ratio, our main aim or focus is to be having higher carbon compared to nitrogen, like 30:1 or 25:1, that is the optimized ratio, so that the amount of yield of biogas that we are going to get from the biomass will be more. Then we come to pH. So what about how will the pH vary with the process? That's what we are going to see. So if you see, initially when your biomass is going to get digested, the acids are going to be secreted, right? Like the acetic acid or kind of butyric acid or propanoic acid or whatever. They are also acid and they also have certain amount of acidity. So these acid will make the feed or the biomass due to feed or the biomass acidic. Acid is going to get generated. Even though they are weak acid, they will induce some acidity to your biomass. So pH will be decreased at the initial stages because of acid accumulation. But once this process keeps happening, all the acids, and when the so the process is going to keep on happening, and this acid is going to be converted to methane. At that time, the pH, as you see, after a considerable amount of time, it will start raising, because all the acids that you generate, that gets generated in the initial stage, will be converted to the methane as well as carbon dioxide. So the acidic content that will be present in your biogas digester plant after a considerable amount of time, that time is what we called as retention time, will be more compared to what you see in the initial case, because initial case only acid is going to be generated, and that acid to get converted to your methane as well as carbon dioxide, it will take time. So when if you check what is the pH of your biomass that is fed to your digester plant at the initial stages of feeding, it will be approximately around 6, because acid is keep on getting generated. But after a considerable amount of time, as I said, all this biomass is going to get digested, the acid is going to be released, and then the released acids is going to be converted to methane and carbon dioxide, the biogas. So at that time your pH is going to increase, because the concentration of your acid inside the system is going to decrease. So at that time the pH ratio will be maintained between 6.5 to 7.5, neither too acidic nor very too alkaline. So the reason why we maintain this ratio is to again make sure that your bacteria that is present in the biomass acts properly, digest the biomass properly. So that is the reason. If it goes below, like let's say too acidic, lot of acid accumulation, then the microbes will be killed. Like as I said in the loading rate, the acid accumulation keeps on happening, and that actually stops the digestion process. So the reason why it actually stops the digestion process is because the bacteria cannot survive under such acidic condition. So as the amount of acid that is going to get generated increases, the acidity will also keep increasing. Like on a layman sense, that's what it is. So if you keep on, acid is going to keep on getting generated, the microbes will not be able to survive. The acidity will be the environment will become more and more acidic. The concentration of the acid is going to increase as we increase the acid content. So the microbes will not be able to survive under such acidic condition, and they are going to get killed. So due to that, digestion process stops. So this is why the pH has to be maintained between 6.5 to 7.5, because that is the proper medium at which your microbes will act effectively, and it should not also be too alkaline. So this is the main principle, and you can see how each and everything is interlinked. Your pH is interlinked to your loading rate and CN ratios also. So if your if you remember, I said if your loading rate is more, if you load your digester more, then acid accumulation will happen. So that will increase the amount of acidic environment. So due to the increase of the acidic environment, your microbes will not be able to feed on your biomass properly, or the microbes will be killed, and due to which your digestion process will stop. Similarly, even if it is alkaline, then your microbes will not have their enzymatic activity, will decrease, and due to which the biomass will remain undigested. So, this is how your pH will have an effect on your biogas yield. Next is nothing but your hydraulic retention time. So, what do you mean by hydraulic retention time? It's nothing, it's just that how much time your biomass feed is going to spend inside your digester plant. So, it is getting fed, digesting, and then it is sent out as spent slurry. That time frame is what is called as hydraulic retention time. So, that usually depends upon the feedstock and the temperature. So, depending upon what kind of feedstock you are using, the amount of biogas that gets generated will be different, and then how much time does it take for the feedstock to get converted or for the biomass to get converted to biogas will change the retention time. So, those two parameters will affect your hydraulic retention time. One is the raw material and the another one is the temperature, and also whether you use a stirrer for your digester plant. So, as I said previously, the biomass and then your microbes will be mixed properly using a agitator or a stirrer. So, if you don't use a stirrer, then what happens is the microbes will not be mixed properly. So, there will not be a proper mix between your biomass and your bacteria. So, the uneven distribution will lead to the biomass being separated into three different layers. One is the floating layer, another one is the fermentation solution layer, and another one is the sedimentation layer. So, the microbes will not be able to uniformly show their action towards all the biomass that is going to be present in your digester if you don't stir properly. So, due to which majority of the slurry will remain. So, if there is a concentration of a bacteria at one particular due to uneven mixing, let's say that there is some amount of the bacteria is going to get concentrated in one particular region, and then the other region is going to remain void of your bacteria, then here more digestion will happen, quicker digestion will happen in the left hand, like in one part, and in the other part there will be no digestion. So, in that case, the retention time, the amount of time that will take for all your biomass to get digested to biogas will increase. So, a proper mixing will enhance your bacteria to uniformly act on the biomass, and that will decrease your retention time or the amount of time your biomass is going to spend inside your biodigester. Next one is nothing but it's the seeding. So, the seeding is nothing but it is just kind of an external catalyst, you can say, is added in order to increase the rate of biogas digestion, to accelerate. Apart from the temperature as well as the pH and carbon nitrogen ratio, it is also that the seeding will help in accelerating your biogas digestion. And then the next one is the toxic substances. Obviously, as we know that the name itself suggests it's toxic, so its presence should be lower, or otherwise they will contaminate or they will kind of harm your bacteria present inside the digester plant, and that will decrease your biogas yield. Also, and the last one is your raw material availability. Based on the type of feedstock that you have, it will affect the digestion process. Some amount of your feedstock, let's say last time if you remember we discussed about the three different types of feedstock: protein feedstock, carbohydrate feedstock, and fat based feedstock. Depending upon the type of feedstock, the amount of biogas that gets generated per unit kg of this feedstock will differ, and the amount of methane that is going to be present in your biogas will also differ depending upon the type of material that we are going to feed inside your digester. So, either let's say like if you use a fat or a protein or a carbohydrate based feedstock, then your ratio of the methane that is going to get generated in the biogas will vary from 50 to 70 ratio. So for, I guess, for carbohydrate or protein, 50-50 is the ratio, like 50 percentage of the methane will be there in your biogas and 50 percentage of the carbon dioxide will be present. Whereas in case if you see for your protein based feedstock or fat based feedstock, then a lot of, like, approximately 70 percentage of your biogas is going to be composed of methane. So depending upon the feedstock also, the amount of methane in your the amount of methane that is going to get generated will be affected. So these are the factors, these are the 8 factors, and I hope you would have got a little bit understanding on what are the different parameters, how they are going to affect your biogas yield. And this is the optimized parameters, like what should be the pressure, what should be the temperature, what should be the loading rate, hydraulic retention time, and etc. So in all these factors, our major aim is to enhance the biogas yield. We do not want anything to be wasted. That is our main concern or main goal. Extract how much ever energy is possible from what we have. That is the goal of this particular discussion. So next we move on towards the digester sizing. So as I said at the initial introduction, I am going to feed in some amount of the biomass to a particular digester, but what is the size of the digester, or how much is the volume of the digester that I require in order to generate my biogas? And that is what we are going to focus from here onwards for the next, I guess, approximately 1 hour 10 minutes or so. So here, if you see, we have a lot of different equations, the energy equations, the volume of the biogas, the volume of the fluid, and the volume of the digester tanks. These are the parameters which we are going to discuss now. If you have any doubts on the previous discussion on the factors, then please ask me now. Yeah, in case if you have any doubt, then you are welcome to ask me now. Okay, then if there is no doubt, then we move on towards the digester sizing. What should be the size of my digester so that for feeding my biomass? First is nothing but how much amount of the energy am I going to get from my biogas. I am using a biomass, feeding my biomass, digesting by my biomass, and I am going to extract energy from my biomass. But how much amount of the energy am I going to extract? And that is what is given by this expression. E is nothing but E is equal to eta times VB times QB. So your eta here is nothing but it represents your burner efficiency. So how much amount of the, so what is the efficiency with which the biogas is going to be generated? The efficiency of the burner. VB is nothing but the volume of the biogas produced from my biomass. As I said, all the biomass that you are going to use will not, like, there is not 100% amount of biogas that is going to get generated from your biomass. So there's a particular volume that is going to get generated. So what is the volume of the biogas that I'm going to get, and what is the heat of combustion per unit volume of my biogas, QB. So this is something that is the energy available from the biogas. But if you see here, we have another expression that is nothing but the net energy is calculated as E equals eta times VB times QM times FM. But the question is, why is there is a, like when I have this equation, let's say this is equation 1. What is the reason for going towards this equation? Like, why do I need to use this equation? So the main reason is because of the methane. So the methane is going to get generated more, and that methane will be helpful for the combustion of carbon dioxide. So some amount of the methane is going to be used up for the burning or combustion of the carbon dioxide, or for the generation of the carbon dioxide. So that is the reason why here we involve these two terms. So QM, that is nothing but your heat of combustion of methane, and that value will be approximately 28 to 29 megajoules per meter cube. So you can see how much amount of heat, how high is the heat of combustion of methane. 29 megajoules, that is 29 into 10 power 6 joules per meter cube. That's a very high heat of combustion. Methane has a high heat of combustion, and FM is nothing but the fraction of the methane that is going to be generated. As I said, the biogas is not just comprised only of your methane, but it also includes your carbon dioxide. So you have to involve the fraction of the methane that is getting generated. That is getting generated in the biogas. Afterwards is nothing but the volume of biogas produced by your biomass. VB is nothing but C times M naught. C is nothing but how much amount of biogas is going to get generated for 1 kg of dry matter that I am going to feed. I feed 1 kg of dry matter. So for that 1 kg, how much amount of the biogas am I going to get? That times your mass input is nothing but is your volume of the biogas. So like we know only we have the standard data values, like for 1 kg of my biomass that I am going to feed as an input, how much amount of the biogas am I going to get. But in a real life application or practical application process, we will not be just using 1 kg, right? So if for 1 kg I am getting this much amount of biogas, so let's say I put 125 kg. So how much amount of the biogas will be generated from that 125 kg? That will be your volume of biogas produced by your biomass, like the full lot of the biomass, how much amount of the biogas it is generating. That is represented as VB. It's not VB per kg of biomass inputs, that is C. VB is nothing but the entire volume of biogas that is going to get produced from your biomass. So that is VB is nothing but C times M naught. M naught is the mass of your feed or mass of the biomass input into the digester. Then volume of the fluid in digester, that is given as M naught by rho M. M naught is the mass of the dry matter that we are going to feed in, and rho M is nothing but the density of the dry matter in the fluid. Afterwards we have the volume of the digester time. So that is given as Vf times Tr. Tr is the retention time, hydraulic retention time. How much amount of time is your biomass going to spend inside your digester plant, and Vf is the volume of the fluid in digester. If you multiply these two, you will be getting the volume of digester in that particular time, because biomass is going to keep on getting generated, right? So that is the reason we have to multiply that with your retention time, and that is what will give you your volume of digested time. So these are the four equations, and we will be specifically using in this session these two equations, these three or four, these four equations. So equation number 2 we will be using, and we will be using equation number 3, equation number 4, and equation number 5. So these four equations we will be using today to solve approximately like 5 or 6 questions that we have. So let's just move on towards questions. So, these are the four equations. Equation number 2, 3, 4 and 5. If you want, you can take it down in your notebook also, because we will be using these equations to solve our numerical problems in the lecture ahead. So this is our first question. Let me zoom in, and this is a very simple question also. We have so let me just read out the question completely. We have a family sized biogas digester that is getting installed, and here our specifications are given. The retention time is given as 40 days. Temperature at which the digestion process is going to happen is 45 degrees Celsius. The biogas yield, that is your C value, is nothing but 0.55. So what this actually means is, as I said previously, for 1 kg of my dry matter that I am going to feed to my digester, I am going to get 0.55 meter cube of the biogas. 0.55 meter cube of biogas is generated from 1 kg of biomass feeded to the digester system. Okay, or let me just keep it as such so that it will be visible. And the burner efficiency is given as 75%. The amount of biomass that is going to be feed in is 20 kgs. So here it is written as 20 kgs, that is the amount of biomass that I am going to feed into the system. So with this, now you can be able to calculate the biogas yield. So that will be nothing but, for 1 kg I am going to get 0.55 meter cube. For 20 kgs I will be, how much I will be getting. So it's just that simple math. And from that amount of biogas, the methane that I am going to get is only 0.7, that is 70% of whatever the biogas is going to be generated will be my methane, that is the FM value. And the next one is the heat of combustion of methane. So the so the methane is going to get combust, so that will be 29 megajoules per meter cube. The density of the biomass feed of the dry matter is 40 kg per meter cube. So based on these specifications given above, calculate the volume of the biogas plant and power available from the plant, and compare if the burner efficiency, compare the power if the burner efficiency is 100%. So what we are going to compare here is, compare the power if the burner efficiency is going to be 100%. So this is the question that is in front of us, and we are asked to calculate two things: volume of the biogas plant and the power available from the plant. So let me just give you some time for you to solve, or come up with the equations that we have to, like, those are the only 4 equations if you see in the previous slide, but how to apply them I request you to first try it yourself before we will solve it in the next 1 or 2 minutes. Okay, I'm sorry. I'll just keep the slide. So this is your question, and yeah, your data, almost all the data is given. You are supposed to use those 4 equations, these 4, equation number 2, equation number 3, equation number 4 and equation number 5, and you are supposed to calculate the volume of biogas and the power available to the plant, available from the plant, like what amount of power is going to get generated from the biogas. So what do you think? What should we like start with, or how should we start with? Yes, any ideas on how are we supposed to start with? So okay, yeah, let's now solve the question. Please interrupt me in between if you are unable to understand how am I approaching the problem. So first let's take here how do you calculate the fluid volume or volume of fluid in the digester. So the formula for volume of the fluid in the digester is nothing but m naught by rho m. So m naught is nothing but the amount of mass input, and rho m is nothing but your density of the dry matter that you are going to like feed into the system. So Vf, that is your volume of the fluid in the digester, is equal to m naught, that is the amount of biomass that is fed into your digester plant, and rho m, this is nothing but the density of your dry matter. So the amount of mass that is going to be fed into your system, m naught, is nothing but 20 kg per day, and the rho m, so this whole divided by rho m value, that is the density of your dry matter, is 40. And for unit for units of dimension, for unit dimension analysis part, I will keep it in the separate column. So this whole divided by and density will be kg per meter cube. So here I am keeping the numerical values, and here I am keeping the units, so that it will be easy for you to understand. So 20 by 40 is nothing but 0.5 meter cube per day. So this is the volume of the fluid in the digester, 0.5 meter cube per day. Now what is the volume of the digester? That is VD we have to calculate. So VD is nothing but VF times TR. TR is your hydraulic retention time, and that is given as 40 days here if you see. So 0.5 meter cube 0.5 into 0.5 times 40. I'll keep the numerical separately and the units separately so that it will be easy to understand. Meter cube per day times day. So 0.5 times 40 will be 20 meter cube, because the day and day since it is meter cube per day times day, so that day and day, that units will get cancelled, so it will be 20 meter cube of the volume of your digester is 20 meter cube. Now we are asked to calculate what will be the volume of the biogas. So VB, that is C times M naught. What is C? C is nothing but 0.55, right? So 0.55 times, and your M naught is 20 kgs. Units will be meter cube per day, meter cube per kg times kg per day. So this value will be, if you can tell me, then it would be great, or let's just calculate. So 0.55 times 20, 11, and here your kg in the denominator, this one, and then this will get cancelled, so it will be 11 meter cube per day. So you know the volume of the biogas. Now you need to calculate what will be the power that will get generated from your biogas plant. So E, or you can even keep P because it's power, so it will be easy to understand. That is nothing but eta, your burner efficiency, times Qm. Qm is your heat of combustion of methane. Fm is nothing but the fraction of the methane present in your biogas, times Vb. Vb is nothing but volume of your biogas that gets generated. So which will be your burner efficiency 75%, here it is written. So if you convert that into fraction, it would be 0.75, and Qm, that is the heat of combustion of methane, is 29 megajoules per meter cube. So let me keep this initially in the same units as megajoules. Fm is the fraction of methane in the biogas, that is 0.7, and volume of the biogas that gets generated, that is 11. So the power that can be harnessed or available from the biogas plant will be 0.75 times 29 times 0.7 times 11, 167.475, but I have not given the units yet. Vb, so here units will be only for Qm and Vb. Qm is megajoules per meter cube, and your VB, that is the volume of the biogas, will be meter cube per day. So this will be megajoule per day, because that meter cube and meter cube will get cancelled. So this is in megajoules per day unit. So this will be the amount of power that can be delivered from the biogas plant in megajoules per day units. Suppose if you want to convert it into SI units, then you are supposed to calculate, so you are going to convert that megajoule to joule and day to seconds. So that will be, so how many joules are present in 1 megajoules? Can anybody tell? How many joules are present in 1 megajoule? Like 1 megajoule is how many joules?
To power 6, I think.
Yeah, it's 10 power 6. So 10 power 6. And so this will be in joules. I'll write that side and the side. And we are supposed to convert, this is per day, so we are supposed to convert it into per second. So we are supposed to divide this. So in a day we have 24 hours and each hour has totally 3600 seconds. So if you divide the numerator by 24 into 3600, you will be getting the units in joules per second. So what will be the answer? You can calculate and let me know what will be the power that gets delivered from your biogas plant. Yeah, I hope this is correct. So the value will be 1938.3680. Let me just check once again. Yes, 38.3650 joules per second, or it can also be written as 1938.3650 watts, because 1 joule per second is 1 watts. So this will be the amount of power that is delivered from the biogas plant, or this is the amount of power what we get from our biogas plant. So it's a very simple problem. You just need to calculate VB and we just need to calculate the power delivered from my plant. And then second part of the question is, if the burner efficiency is 100%, here our eta value is 0.75. If the eta value was not 0.75, if it was 1, 100% means 100 by 100, if it was 1, then how much amount of power will we be able to harness? So that is, so here it will be just 29 times 0.7 times 11. So you are just supposed to remove that factor. So this will be the amount of power that will be delivered from the plant. So you can compare and check how much is the percentage of difference. Approximately like 25% of my heat is going to be wasted. Whatever the power that I'm going to get, or that is getting delivered from the biogas plant, is going to get wasted as heat. Instead of harnessing approximately around 223.3 megajoules per day, I am getting only 167.47 megajoules per day. So this is one of my limitations that I have, that due to my burner I am going to lose a certain part of my energy there. So if, let's say, if I come up with a burner design or with a material through which I am able to enhance my efficiency of the burner, then it will benefit me at the end of the day, because this is approximately 25% of the heat is going to get lost in the burner. So I'll be even able to use that up if my burner efficiency percentage would have been 100. But due to the material limitations and the geometric limitations that we have, the burner efficiency is not, we are unable to achieve the burner efficiency of 100%. It remains in 75 to 80 ratio, and due to which we are losing some amount of energy that we are supposed to use it for our purpose. So this is kind of like a comparison to just show how burner also can, or how various parameters can affect the amount of heat that you actually gain from the system, gain from the biogas system. So this is the second question, very similar question, and so I think you guys will be able to solve this. So I'll give you some amount of time, like let's say approximately 5 minutes or some time for you guys to solve and let me know the answer, because here you have options also. So since you have the options and all the data is available, I expect you to solve. The pattern remains the same as what we have followed for this. Over there we even calculated VB and VD as well as VF. Here you are just asked to calculate the power that is available from your digester, and you have 4 options: 16.2, 24.3, 32.3 and 48.6, and no need of unit conversions also. It's a straightforward question. So I think you can solve this question and let me know the answer, which is the right option. I'll give some time. And I hope the question is also visible. Let me make, yeah, I've zoomed in so that you can see the data clearly. Same question, similar pattern, nothing much to change. Over there you are even asked to calculate the volume of biogas. Here the question does not ask you to calculate that also. It's just that we need to calculate the power available from the digester. Of course, in order to calculate your power, you need the value of VB. So that is like within the process of calculation, you will be calculating that as well. So what will be the answer? Similar approach, nothing much different here. A very small change, that's all. Nothing big or nothing different. A very small change in the question. And you can, like here the only thing that is going to be different is your m naught value. So I am giving you that hint also. So what is going to be different? Your m naught will be different. I mean, you have to calculate your m naught here. It's not straightforward. It's not given in your data like in a straightforward manner. Over there, m naught was given as such as one of the specification. Here the datas are given, but you are supposed to calculate. It's not present in the, it's not present here. If you know your m naught value, then the entire process remains the same. So what will be the value of m naught? Yes, what will be the value of m naught? Anybody? So what is actually m naught? We discussed this term, right? So what understanding do you have? Yes, yes. Hello? Yes, I guess.
Sir, 20 kg per day.
I mean, how did you come up with the value of 20 kg per day?
No, sir. No, sir. Actually, sorry, 2 kg per day.
Okay,
Dry matter consumed.
yeah, so that will be the amount of dry matter consumed. So that is your value of m, right? So that is, you are saying it as 2 kg per day.
Yes, sir.
Yeah, but the thing here is that 2 kg per day is for one cow, like it's for one single head, but we have the number of cows is 5.
One also it is about 10.
Yeah,
10
yeah,
kg per day, sir.
yeah, exactly. So now you know the logic. So m naught value was the only one thing different. So can you tell me what will be the value of VB and power available from the digester?
Yes, sir. Sir, first we calculate the VF. VF is
Yeah, uh, yes.
10 meter cube.
I'm unable to actually hear your voice. You can type it in chat box also. If
Sir, 10 meter per cube.
now VF is, what is actually VF? The formula is m naught by rho m, right? And rho m is nothing but your density,
VF is m naught upon
rho m. So what is your value of m naught?
per meter cube.
Yeah, m naught is 10
Sir,
k.
10.
Yeah, and rho m, rho m is 50 kg per meter cube, right? So your VF is nothing but m naught by rho m. So that will be 10 by 50. So 10 by 50 will be 0.2. So that will be 0.2. VF will be 0.2. Honestly, you don't need to actually calculate VF and VD, because we are here, we are not asked to calculate the volume of the fluid in the digester or volume of the digester. So you can even start your calculation from the volume of biogas itself, but it's just for practice purpose we are solving volume of your digester also here. So let's just, and meanwhile if you are actually calculating, then either do let me know the answer, or you can also type it in chat box. So Vf is nothing but m naught by rho m. Here m naught is 2 kg per day, but this is only for one single cow. But we have totally 5 cows. So the total amount of dry matter that is going to get generated will be nothing but 2 times of 5, so 10 kg per day of dry matter will be generated from all the 5 cows. Rho m is nothing but your density of the dry matter, that is 50 kg per meter cube. So Vf will be 10 by 50. I am not going to write the units because we have previously solved by separating the numericals and then the units and dimensions, and then I have shown that how to do that particular process. So here I will just write the units side by 0.2 meter cube per day. This is the volume of the fluid in the digester. Volume of the digester will be nothing but volume of the fluid in the digester times the retention time. So Vf is 0.2 and your retention time here is given as 20 days. So that will be 4, right? 20 times 2 will be 4 meter cube. So now comes the important part, volume of the biogas, that is C times m naught. What is your value of C? C is nothing but 0.24 and m naught we calculated here as 10. So that will be 2.4 meter cube per day. I hope you got this same value for your same value as your answer also. In case of any discrepancies, then do let me know. We will discuss where we are going wrong, or am I going wrong anywhere, or we will discuss that out. Is it the same value that you are also getting? VB as 2.4 meter cube per day.
Yes, sir.
Okay, thank you. So power will be nothing but burner efficiency times Qm, that is your heat of combustion of methane, times your Fm, that is nothing but the fraction of methane in your biogas, that times your volume of the biogas that is going to get generated from this process. So your burner efficiency is 60%. That 40% of our energy is going to go for as wastage. So 0.6 times heat of combustion of methane is 28, here it is given. I am going to keep it in megajoule units itself, since the options here are in terms of megajoules. Fm, that is the fraction of methane, is 0.8 times Vb, that is 2.4. So can you tell me what answer you will get if you multiply all these 4 terms?
Sir, 32.256.
Okay, yeah, correct. So megajoules per day, the units will be in day, and since here our options are also there in megajoule per day, so the option is C.
32.3.
Yeah, 32.3 megajoules per day. And if you see, this question was asked in UPSC civil service exam in the ESCE branch in 2019. So yeah, that's just additional information where these kind of questions, like You can also check for the papers, and then if possible, if you get similar type of questions, then you are always welcome to solve those. Next question, this will be quite different from what we have seen previously. So here we are actually constructing a community type biogas plant, and we have a village with 85 families. So here we are going to use pig manure as a waste, and that is what is going to be our biomass feed to the digester, and every day we are approximately feeding 410 kgs of pig waste, and then this pig waste is going to be there inside your biomass plant for approximately 35 days, and then the density of the slurry or of the like the water and then the pig manure combination is 1110 kilograms per meter cube. They are asking you to calculate the minimum working volume and actual volume of the digester, and that should be 10% more. Considering the actual volume, they are asking you to calculate the height and the diameter of the digester. Here if you see, I have given it should be 10% more, right? So why is this 10% we keep it more is to provide, it's a kind of a provision that we give to the digester for the biomass, for the biogas accumulation. So the biogas that's going to get generated, we provide a certain amount of space for them to be stored. So that is this 10% of the volume of your digester will be allocated for this biogas storing or accumulation. And with this as our data, we are asked to calculate the minimum working volume and the actual volume, and from the actual volume we are asked to calculate the height and the diameter of the digester. One data that is I forgot to mention here is that your height of the digester is going to be 2 times greater than that of your diameter of the digester. So this is the question. Now we are asked to calculate the minimum working volume, the actual volume, the height and the diameter of the digester. So what is your thought process on this? So let's just solve this question. So quantity of the, so how much amount of the waste or the pig manure is going to be fed into the digester? That is 410 kg per day. This is nothing but this will be your you can keep it as m naught. Now to this, so here there is one particular condition that whatever you take as your manure or the slurry or whatever you are going to take it as your waste, you have to add equal amount of water to that in order to make your slurry. So if we add equal volume, so that is again 410 kgs, right? So the total weight after addition of water will be 410 times 2, because 410 is already present, which this is nothing but is your dry matter weight, and you're going to add same equal quantity of water, so that is again another 410. So 410 from dry matter or the pig manure or the pig waste plus another 410 from water. So that will be total will be 820 kg per day. So you know the weight, you have to calculate the volume of the digester. So that will be this divided by density will give you the volume. Will be nothing but 820 times 1110, that is your density, right? So let's calculate that. 0.7386,
Sir, 0.7386.
yeah 0.7387. What will be the units? Meter cube per day, because 820 is nothing but for one day this, yeah, so 820 kg per day, and this will be kg per meter cube. So the volume of the waste that is going to be there in your digester will be 0.7387 meter cube per day. This is for one day. Yeah, so we have to take it for 35 days. Because our retention time is 35 days, right? So 0.7387 times 35, and that value will be
25.85, sir.
yeah 25.855, and this will be in meter cube. So this is the minimum working volume of your digester. Now we need to calculate the actual volume. So for the actual volume, what is given is it will be 10% more compared to the volume of your minimum volume of your digester, because of that provision that we provide at the top, right? So this value has to be multiplied with 1.1. $28.4405. I hope you are getting why we are using this. The reason why we put 1.1 is because of the additional extra 10% that we are giving it as a provision on top of the digester, so that the biomass, that biogas that gets generated can be accumulated or can be stored there. So that is the 10%, if you see. So that value will be 28.4405, and this one will be your minimum working volume of So volume of the digester, and then the volume of the slurry or the volume of the waste that will be in the digester will be the same under the working condition. This will be the actual volume of the digester. So we know the actual volume of the digester, and if you see majority of the digester over here, let me go to the very first diagram. It will is approximately cylindrical in shape, right? So we take the design considerations of, or the design of the digester here also as a cylindrical design. So let's take the our digester that we are using as cylindrical in shape. So what is the volume of a cylinder? It is either pi, that I am writing it as 3.14, pi r square h or pi d square h by 4, right? So pi d. So here, since it's already given that your height of the digester is 2 times that of the diameter of the digester, so h will be nothing but 2 times of d. That's what it means. Your height is going to be 2 times that of the diameter of your digester. So if you substitute this h is equal to 2d in here, then you will be getting volume of the cylindrical digester as and this volume of the cylindrical digester is nothing but is the actual volume of your digester. So that will be 28.4405 meter cube. So from here you can calculate the value of d. So what is the value of d actually you are getting? So this will be it will be 2. So this will be your diameter of the cylindrical digester that we are going to use for our process. So let's just calculate that. 28.4405 times 2, the whole divided by 3.14, whole power 1 by 3. Sorry, 18.1111, right? 18.11. It would be approximately 2.6260 meter. Diameter will be 2.620 meter. I hope this is the same answer you are also getting, and h will be nothing but 2 times of this diameter. So 2 times of 2.620, so that will be 5.24 meter. So this is the diameter of your digester and this is the height of the digester. Well, it depends upon you. Even you can take it as a spherical digester, then in that case it would be just 4 by 3 pi r cube, right? So if you take it as a spherical digester, volume of a sphere is 4 by 3 pi r cube or pi d cube by 6, and then you can calculate and get the value of d, that is the diameter of the spherical digester that you are going to use. Here I have taken the digester to be cylindrical in shape. So I hope you don't have any doubts related to this question. If in case if you have, and then do let me know before we proceed to the next question. This is a very simple question which you can actually solve. So what will be the answer for question number 4? Yes, this we did it even in the second question also. We have seen similar problem there while calculating the value of m naught. So it's simple. Here you have the manure production rate is 15 kg, but that is for one day and for one head. That is, one head here means one cow. So we are supposed to calculate for 420 cows how much is going to be the manure production rate. If I get to know how much is that for 420 cows, then I will be able to calculate my gas formation rate. So that's simple. So let's calculate that also here.
1859.41.
Can you tell me how you got that value?
Sir, basically is a 420 cows,
Hmm.
and for the manure is per
Yes. Hello.
yes sir.
Ah.
So I multiply the 420 multiply by the 15 and divide by the density.
w-
A
Uh,
cow manure is 0.34
no, 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 no.
meter cube.
Yeah, yeah, yeah. Okay, okay. I'll just see here. So up till that first part, it is correct. So if you multiply that 15 times 420, you will be getting 6,300 kg of manure per day, right?
63. Yes sir. 6,300
Yeah.
kg.
So this much
Yes
amount
sir.
of,
Yes sir.
yeah, yeah. So this much amount of manure is going to be produced. Let's leave that per day stuff for some time. Let us consider that we are having only one day. So 6,300 kg of manure is going to be produced, right? And here it is written that the gas formation rate is 0.34 meter cube per kg of dry matter. So what that means is 0.34 meter cube will be generated for 1 kg of my manure, right? So for 1 kg of my manure I am going to get 0.34 meter cube. I have I have 6,300 kg of manure of my manure. So how much amount of biogas am I going to extract out from this manure? So that is nothing but 0.34 times 6,300, right? That value will be 2142 meter cube of biogas. And since the entire calculation is for one particular day, it is per day. So the answer will be 2142 meter cube per day. Here we have to multiply. This is not density. So density, and even if you can see density's unit will be kg per meter cube. It's meter cube per kg of the dry matter. So you can either way you can understand and then solve the problem, but logically speaking this is what is the solution. So for 1 kg of my manure or 1 kg of my dry matter I am going to get 0.34 meter cube of biogas. I have totally 420 cows and each cow is going to generate 15 kgs. So I have totally 6,300 kg of my manure available with me. So how much amount of biogas am I going to get from this much amount of manure? So this is the answer, 2142 meter cube per day. And suppose if they ask you how much amount of biogas will you be generating in 20 days, then in that case it would be 2142 times 20. I am not sure what the value will be. Approximately it will be 42840 meter cube if I am not wrong. Yeah, 42840 meter cube. This will be the amount of biogas that will get generated after 20 days of generation. So I hope you got that particular clarification of what you were looking for. So here we do not divide that 6,300 by 0.34, you have to multiply that with 0.34. So let's come to our So let's come to our final and last question. Actually this is a quite lengthy problem, so but anyway let's just solve this also. Here we have an engine generator that has to be powered using a biogas plant, and the total power requirement for that particular house or whatever, that engine generator, or from the engine generator is 2560 watts per day. Now we are asked to calculate the volume of the digester unit if rice husk is used as a biomass material. The calorific value is given in terms of kilocal. So here you need to actually convert that kilocal to kilojoule, and then you are supposed to find out the volume of the digester unit if the rice husk is used. So what is the thing is, so we are given with certain data. So the value of C, which is nothing but how much amount of the biogas is going to get generated per unit of dry matter that I am going to use, which is 5.67, and in 1 kg of the fresh waste I have approximately 10% of dry mass, dry biodegradable mass, and the volume of the fresh waste gives approximately 0.56 liters of biogas. An equal amount of water is added to the slurry. Retention time is given as 33 days. So this is the equation. Here we are having fresh waste. Over there all the calculations that we did previously was for a dry waste. Here our waste is a fresh waste. So in that case, how we are going to solve? That is the question that we have. So let's just solve this. So we are supposed to generate 2560 watts, right? That is what is the power requirement. So, but unfortunately what happens is that the engine generator that I am using is not 100% efficient. The generator efficiency is 75 and that is only 45, the engine efficiency. So how much amount of the power should be input so that at the end I am going to get this much amount of power as the output? So that is what we are supposed to identify first. So this is nothing but the output power I want, output power that I want. So and my generator efficiency and my engine efficiency is not 100%, is not 100%. So suppose if it was 100%, then the input power will also be same as 2560 watts. But since it is not the same, it has certain values. So how much amount of the input power that I have to give? Because this input power is nothing but should be the amount of power that we will get from the biogas, because this biogas is what is going to run the generator and supply the power to us. So if I have to get this much amount of power, what will be the power that has to be fed to my electrical generator before? So input power to my generator times the generator efficiency, I guess that is 0.75, and my engine efficiency 0.45. After this much amount of my input power is lost, whatever the power is I am going to get out is the output power, and we know the output power as 2560 watts. So if we know this, then we can calculate the input power, right? So input power will be divided by 0.75 times 0.45. That would be approximately 7585.1851 watts. 7585.1851 watts. So my biomass, which is going to operate my engine generator and deliver a power of 2560 watts, should supply a power of approximately 7585.1851 watts. This much amount of the power biomass is going to give, like the input, the biomass energy or power, or my biomass has to generate this much amount of power. So if my biomass has to generate this much amount of power, how much biogas I require? Biogas has to supply 7585 or 7585.1851 watts power to my generator. If this is the case, then how much biogas will I require for supplying this much energy will be required, right? Now we are supposed to calculate the biogas volume. We know the calorific value of power will be biogas volume will be equal to input power, that is 7585.1851 divided by 20,000 times 4.18. So this value will be it's 20,000. So or let's say, since this value is extremely very small, let's take it as 20 kilocal and then solve. So I am taking here it as 20 kilocal or 20,000 calories, so that we can eliminate the power, like it's coming in 10 power minus 5, right? So we can eliminate that out. So 0.0907 will be our biogas volume, meter cube per second. The volumetric flow rate will be this much amount of biogas will get generated. So then this is for 1 second. So we are supposed to calculate this for 33 days, right? Because our retention time is nothing but it is 33 days, if you see here. So like this we have to keep calculating. So total volume of biogas that will be generated will be equal to 0.0907 times 33 times so here we have to calculate this. So let me just stop this problem here and then let us take up this problem tomorrow, because we are already past our timelines for today. So let's just stop our problem here. We will continue this problem in the next class. Before we begin our week 9 session, we will solve this problem first and then we will start off with our regular discussion session for week 9. So let me just stop sharing. So yeah, I hope if there are any doubts, then please let me know now. If in case if you have any doubts, due to time constraints, we have actually kept the last problem alone. We have solved it for halfway through. Actually, I didn't check the time. it was already past 7, so that's my mistake. So we will solve this question in the next class before we begin our week 9 live session. So if in case if you don't have any doubts, then can we conclude the session? Okay, so I think there are no more doubts, so let me just conclude the session for today. I thank you all for joining this week 8 live interaction session this Sunday afternoon. Our next week 9 live interaction session will be on 24th March during the same time 5 p.m. to 7 p.m. I also take this as an opportunity to thank both Professor Vaibhav Vishant Gaut sir and Professor Ananda Lakshmi ma'am and the NPTEL team for giving me this opportunity to interact with you all in this Sunday afternoon. Next week we will take up with this question that we have solved today halfway through. We will finish this question before we proceed to the week 9 live interaction session. Till then, if you have any doubts, then please let me know either through the ask a question tab or through the email ID given in the presentation, the very first slide of the presentation. I will answer to your questions as soon as possible. So if in case if you have no doubts, then happy afternoon, and yeah, so bye.